This lecture is actually the continuation of the previous lecture. In that lecture, we discuss about the magnetic flux, and we know that magnetic flux is represented by this phi, which is actually the number of magnetic field lines that are passing through the area, which is present at some angle to external magnetic field. We call this as a magnetic flux, and we know that if the area is present parallel to the external magnetic field, then in that case the magnetic flux is zero, and when the area is present perpendicular to the external magnetic field, in that case the magnetic flux is zero. So here the magnetic flux depend upon the magnetic field intensity, the magnetic induction, and the area which is exposed to that magnetic field lines, and it also depend upon the inclination of the area with the external magnetic field. And here in this part of the video we will only focus on the magnetic flux through a closed surface. So here we have the closed surface, this is also the closed surface, and this is also the closed surface. If the magnetic field, if the magnet is present inside this closed surface, if the magnet is present inside this closed surface or inside this closed surface, so this is not necessary that the magnetic flux will be present inside this closed surface. Sorry, the magnet is present inside this closed surface. The magnet may be present here, may be present here, may be present here, but I mean that the magnetic field lines are producing from this magnet will pass through this closed surface. Okay, so here if I consider the magnet inside this closed surface, so the magnetic field lines will pass from the each part of this sphere. So here we divide this whole sphere into small areas, so which is given by this. So this is actually the let's say we consider this part of the sphere and we zoom that. So this is the zoom part of this sphere. So here if we see carefully, we divide the whole sphere into small areas. So these rectangular areas are a large number of rectangular areas on this closed surface, and similarly we have the large number of rectangular areas on this surface, and we can divide this into large number of small areas. We call that area as del A. Del A. So here this is del A, del A1. This is del A2. This is del A3. Similarly, this is the del A4, and in this way we divide these are up to del AN. And similarly, we have the so the magnet is present at the center of this sphere. The magnetic field lines will passing perpendicular to each part of this sphere. So here from this sphere to this area, this magnetic field line will passing perpendicular. So here we have let's say del A1. The magnetic field line will pass perpendicular to that del A1, and if we have del A3, the magnetic field line due to this center magnet will pass perpendicular to through this curve. And similarly, this is the other area, so the magnetic field lines are also passing perpendicular to this area, and these are the different areas I have selected such as this. So here we know that if we put the magnet at the center of this sphere, the magnetic field lines will passing perpendicular through this area, and similarly that are passing perpendicular to this area, and that is perpendicular through this area, it is perpendicular to this area, and similarly for each areas, and the magnetic field line due to the center magnet will pass perpendicular. So for the closed surface, for the closed surface, the magnetic flux is given by flux is equal to for the closed surface. So the magnetic flux through this area, through this part, plus the magnetic flux through this other part. plus the magnetic flux through this other part, and similarly we will take the all parts, the all small parts of this sphere. So this will go up to phi n. And we know that the formula of this phi, so phi up closed is equal to, this phi is equal to b uh, del a del a1 cos theta plus b del a2 cos of theta plus b del a3 cos of theta plus the b del a4 cos of theta plus up to b del a n cos of theta. As we know that, let's say we have this area, okay, this area will have some magnitude. The magnitude of the area is given by the length multiplied width, and the direction of the area is always perpendicular to the area. So here is the direction of the area. This is, let's say we have the direction of the area, and similarly the direction of the the direction of the direction of the magnet is also perpendicular to the area. So here, this is the direction of the magnet, and which is also perpendicular to the area. So this is the direction of the magnet. This is actually the direction of the uh, magnetic field line. So this is the direction of B. Okay, and this is the direction of A. So here, between the direction of B and direction of A, theta is equal to 0. So for each part here, for each part, the magnetic field lines is perpendicular to this area, and the direction of this area is also perpendicular. For this, the direction of the area is perpendicular to this area, and the magnetic field line will also pass perpendicular through this area. As theta is equal to 0, this equation will become phi of the closed is equal to, here b del a1 cos of 0. Cos of 0 is equal to 1. So here I'm going to write that cos of 0 will be equal to 1. So this will be equal to this plus b del a2, b del a2, and cos of 0 is equal to 1 plus b del a3, cos of 0 is equal to 1 plus b del a4, cos of 0 is equal to 1 plus up to b del an cos of 0 is equal to 1. Phi of closed is equal to summation of B magnetic induction and del A. So B is this, and summation of del A, the flux of the sphere, is equal to B, and the summation of del A here is the 4 pi r square.